and just how sound moves through things. First, we got to go over the quick review, which reviews the Notes 5A from the other day. Here we go. If you haven't done this already, pause the video, fill it in, use the word bank down here, and then unpause it and check yourself. All right, so sound travels in waves called compression waves, which require the vibration of particles to move sound energy. Wavelength is measured by seeing how far it is from one part of a wave to another repeated part of the wave. So that would be crest to crest or trough to trough. Frequency is measured by counting the number of complete wavelengths out of time. The speed of sound depends on the medium it travels through. That material's TED, temperature, elasticity, and density. Now we got a longer line here, so I'm going to put temperature down here. Temperature, elasticity, and density. All right, pause it if you need to get that written down, but I'm going to clear it and move on. All right, yesterday. It's always, I put that on there, famous last words. But anyway, yesterday we said that there were 3 things that had to be taken into account when discussing the speed of sound. And what's the guy's name to help us remember that? Ted. Ted's his name, and it is temperature, elasticity, and density. Now, we have talked about temperature for an entire unit. We did our whole last unit on thermal energy. We've done a lab on density. We've calculated density. We've talked about density before. So the only one of these that we haven't talked about a bunch already is elasticity. Now, you know what elastic is and you know what it does. It stretches. But then when you let go of it, it returns to its original shape. And that's what it means for something to be elastic. Elasticity is the ability of a material to bounce back. That's why rubber bands stretchy, bouncy. The ability of a material to bounce back after being disturbed. So a rubber band has high elasticity. When you stretch out a rubber band and let it go, it returns back to its original shape. It snaps back to its original shape. You don't have to coax it back into it'll snap right back. And that's why it can be used to fling things. Do you need to move as well? Or maybe I can move this back some. Does that help? Okay. So when you stretch it and let it go, it returns to its original shape. One day it'll pop up. All right, so something like Play-Doh, however, has low elasticity. If I take some Play-Doh and roll it into a snake and stretch the snake out, is it going to go back into its original shape? No. It does shrink back some, though, doesn't it? Have you ever noticed that about Play-Doh? If you try to flatten it all the way out, it kind of comes back a little bit. It's a little bit elastic, but it definitely doesn't go back to the shape of the can once you dump it out of the Play-Doh can. When you smash it, it doesn't go back up into can shape. Wouldn't that be crazy? Yeah. Mm-hmm. I'm sure they've made something that does that. So has this just stopped working altogether? Right? Well, can we pause? Okay, so rubber band has high and Play-Doh has low elasticity. When you stretch it out and let it go, it doesn't go back. Let's just stick with that. Going once, going twice. All right. Sound travels more quickly in mediums that have high elasticity because when the particles are disturbed, they quickly spread out again to carry the vibrations. Solid materials are usually more elastic than liquids or gases. Solids carry sound better because the vibrations do not have to travel as far to pass the energy of the sound vibration on to the next particle. And I think I probably wanted to say particles or molecules there instead of vibrations. Yeah, that makes more sense. The particles do not have to travel as far. That makes a lot more sense. Yes, I wrote these notes, but it was 10 years ago. And I've had kind of a rough week, especially a rough week on my brain. All right, so solid materials are usually more elastic than liquids or gases. We did that. All right, liquids carry sound well, but not as well as solids. Gases are the least elastic, and the particles are spread far apart. So they are the poorest transmitters of sound. All right, I know y'all have seen this before in cartoons or whatever, when the opera singer gets the glass and sings at it and does what? Right, he breaks it. So this actually was a party trick that opera singers used to do back in the day before Xbox and before TV was even that popular. You'd go to a dinner party, and if you were a singer and you could hit the note, and it's all about resonance. Okay, so what is this guy doing? Trying to break the glass with his voice. So all objects, I'm French all of a sudden. All objects resonate naturally. You know that the particles are moving, and they don't stop moving until you get down to 0 K. So as long as you're at room temperature, even though it's a solid and we can't see it, the particles are moving. So these vibrations are so, what's the word that I use? Don't remember. Oop, didn't put it in there. Frequent. That's the word. These vibrations are so frequent that we don't even see them. So they are moving in there, those little particles, but it happens so fast that we don't see it. So if the frequency of the sound that's being produced matches the natural frequency of the object, the sound waves can add to those natural vibrations. So what that singer is doing is he probably went, into the glass and listened to it, got the note in his head, and then took that note and amplified it as loud as he could, and it made the natural frequency of that glass resonate to the point that it broke. And that is called resonance. Resonance occurs when the frequency of the sound waves and the natural frequency of the object are the same. The most common example of this is with the crystal stemware. Like that's what we're most, but also musical instruments. Musical instruments are. But if he has the frequency, if it matches the frequency of the sound that is being made, it can break the glass. So I'm not going to break the glass, but I am going to make it resonate. Please put the crumbles away. We don't need it right now. And I'm also going to use warm water. Why am I going to use warm water? Right, because the particles are moving faster, and I want the particles to be moving as fast as possible. So I'm going to, even though the glass is clean, I'm going to get it warm. I'm going to put some warm water on it. And with that, I can make it resonate. Got too much lotion on my hands. It's not working very well. There we go. Anyway, that's the natural frequency of the glass. We can't do it these days. I used to into it and have a child listen, and you can hear it resonating. But that's as close as we're going to get these days. And y'all have seen people play the glasses, right? With different amounts of fluid, makes it resonate differently and makes a different note, right? Okay, so I could, if I did this fast enough, break the glass, but I don't want to. All right. I know that this won't work at home. So if you are watching this video at home, you've got to go back to Schoology to watch the video that we're getting ready to watch because it's not going to record well. They've got some kind of a thing on it that makes it so that if you play another video on Screencastify, it makes the sound do funny things. So we're going to watch a video of a glass being broken. You've got to go back to Schoology to watch yours. All right. So we just watched the videos. Hopefully you watched them too. Another common example of resonance is musical instruments. So the reason that musical instruments work is they take advantage of resonance. You figure out the natural resonating tone of the instrument, and you figure out how to hit on it or blow across it or pluck a string or strum or something and create vibrations within the body of the instrument, and that creates resonance. That's what resonance is those vibrations being increased. And then finally, there's the Tacoma Narrows Bridge. This does not look real, but I promise you it is. This does not look real, but I promise it is. It's so crazy. So back in the 1940s, they built this bridge across the Tacoma Narrows Sound, which is in Washington, Seattle, near Seattle. And well, near Tacoma, but anyway, between Tacoma and Seattle. And the angle that they built it at when the fall winds started blowing, when they hit 40 miles per hour, it matched the exact resonance of the materials of the bridge. And the bridge started swaying and didn't stop. And it shook itself apart. Now, there's a couple of things I need you to know before you watch the video. Number one, which you're going to have to go back to Schoology to watch, you at home. So number one, you need to know no one got hurt. A dog did die, though. There was one woman who was in her car in the middle of the bridge. When it started shaking so much, she got scared. She got out. She got in someone else's car to drive off of the bridge. And then remembered her dog was in the car once she got off the bridge. The man who designed the bridge wanted there to be no casualties, so he walked out there to try to save the dog. The dog bit him and fought him, so he said, "Never mind, dog." So the dog did die. Like when the bridge falls and the car falls, there is a dog inside of the car, but that's the only casualty. What's amazing is that there was a guy who had just gotten a camera, like for his birthday, who lived on one side of the bridge, and so he got out there and filmed the whole thing, even though this was 1940-something. Also, I need you to know that it's going to seem fake because of the way it's presented. But I need y'all to understand that when people went to the movies in the 40s and 50s, there was going to be a cartoon before the feature. There was going to be a newsreel before the feature. And this little clip we're going to watch is from the newsreel. Now, if people have paid their 50 cents, I know that seems crazy to pay, but if people have paid their 50 cents, which was a lot of money back then, are they going to be happy with a newsreel that's just a talking head, just blah, 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 blah? No. So there's music that sounds like an... And there's all kinds of stuff that makes it seem extra. So go watch it. They did rebuild a couple of years later. They built it at a slightly different angle, and it's still standing today. So it was just the angle that they chose and the way the wind was blowing. It amplified the natural resonance. It's called mechanical resonance. There's a truck. I believe it's a Dodge Ram. No, I don't know. There's a big truck. It's a diesel thing that gets a mechanical resonance problem. When you hit a certain speed, it goes boom, boom, and you got to like slow down and get it re-geared and get it back down to first gear and then go back up and you're fine. Anybody ever experienced this in a larger vehicle? Yeah, it happens. There's a certain truck that does it, and yeah, it's a thing. It's called mechanical resonance. All right, so when the wind reached certain speeds, the frequency of the vibrations was the same as those of the materials it was made of, and it vibrated to the point of collapse, just like the glass that the opera singer shatters. So there's link as well if you're at home. Really? Is this what we're doing today? This is what we're doing today. All right, so we have discussed wavelength, which is the distance between corresponding parts on a wave. And we have discussed, come on. Why you gotta be like that? We have discussed wavelength, the distance between corresponding parts of a wave. And we have discussed frequency, how often the waves happen, how many complete waves we get in a given period of time. So those were the two vocabulary words from yesterday. So now we've added resonance, and now we're going to talk about amplitude. So another way to measure a wave is its amplitude. And we've already talked about the fact, what do you do when you plug your guitar into an amplifier? What happens to the sound of the guitar? It gets louder. So amplitude is the maximum distance. I don't know, it sounds like a superhero to me. Amplitude, going at maximum distance. I don't know. Anyway, the maximum distance the particles in the medium carrying the wave move away from their rest position. It measures how much a particle in the medium moves when disturbed by the wave. So if it's a quiet sound, it only moves the particles a little bit. But if it's a loud sound, it moves the particles a lot. Science. Okay, get that written down. All right, so here in class, we've got some slinkies, and I'm going to give the directions to the people that are in the room, and I'm going to be doing it too just by myself. All right, so the first thing I want you to do is make a transverse wave. So just need to move it up and down so that you get that crest and trough of a wave. Everybody got a transverse wave? Good. All right, now I want you to try a compression wave. So one of you is going to hold still, and one of you is going to push and pull, and that's going to give the compression wave. Okay, so now go back to that transverse wave and give me a transverse wave with a low amplitude. So where it doesn't get very far from rest. All right, now give me one with a high amplitude. What do you have to do to get it to have that higher amplitude? Right, you got to put more energy into it. Lovely. So to get greater amplitude, you have to use more energy. Thank you very much. So that means that amplitude is a direct measure of a wave's energy. So the louder a sound is, the more energy it has. And doesn't that make sense? It doesn't take much energy to talk like this. It takes more energy to talk like this. You have to put more energy into it to get it to amplify. Going once, going twice. All right, so which one has the greatest amplitude? A, B, or C? I know it's a little easier to see on my sheet because I've got colors. Which one has the greatest amplitude? A, because it's the one that is the furthest from rest. Which one has the least amplitude? Because it is the least amplitude and the smallest thing from rest. All right, it is a little harder, going once, going twice. It is a little harder to tell on this one. It's a little harder to tell on a compression wave. But if you're thinking about that compression wave as that sound of me, if I go, how did that reach your ears? Because I made such a loud, sharp sound, those air particles are going all the way to your ear and then pat into your ear. And that's what makes that sharp sound. Now, it happens fast. Now, if I go, you still can hear it, but did I disturb as many air particles? So that louder sound disturbs more air particles. So you've got more air particles in the compressions. That quiet sound disturbs fewer. So which one has a greater amplitude? Which one's louder? B. Why? Because it's got more particles in compression. The rarefactions might well be empty in a loud sound. Where in a quiet sound, you're going to have some particles in the rarefactions. All right, I believe that's it. Have a lovely day. Make good decisions.